In today's lab exercise, we're going to continue with this analysis of the contraceptive use data with regression analysis. So you'll recall last time we did our exploratory analysis, created a table 1 and a nice bar plot, and now we're going to continue doing some calculations with the data. I'll go through here's the list of questions. I should say if you want a built version of this that shows all of the results, it's available on our website. That is, let's see, I'll type it in. It's bios2.waldronlab.io. You can find the built version of this. You can also probably build it yourself if you are running this either on one of the online services where I have it set up or locally by pressing the knit button. But I'm just going to run it interactively here. So I'm going to start by loading the data. Oh, does not exist. That's because I'm in the wrong directory. Common problem that I see with new students. So this is, and with myself. So I'm in the session 3 directory, but this is in the vignettes directory. You can usually solve this by going sessions, set working directory to source file location. If I were knitting, it doesn't matter because this is always in the source file location, but for interactive use, it does matter. Okay, so I've loaded the data set now. Remember, there are some parsing failures that has to do with extra space and extra space at the top, but it actually is okay. If we look at view cues, note that up here I have permanent code. This is code that I want to go into my final program. Things like view, I don't put up here because that's just for my interactive use. R is great for interactive data analysis, and you should do that, do it lots. But for your program, this part that goes up here, keep that to just things that actually do things or show things to your audience. So when I do view cues, this is nice. I can see that the data set looks like I expect. It loaded like I expected. That's great, but I'm not leaving view cues up here. I do leave summary cues because this looks like something nice to show. And recall in the last session, this sort of complicated code for loading the data set. I didn't write all of this myself. I did this using file, import data set, and then from base or from text read R. And I'll just note here as you're starting your own analyses, especially for those finding their own data sets, there are other options here that are pretty useful, like from Excel, from SPSS, from SAS, and from Stata. This makes it much easier to import from all of these sources than programming this yourself. These things work well. Okay, first question. What is the mean fraction of women using birth control for each age group, each education level, for women who do or don't want more children? This is the kind of question. It involves grouping some rows together and then doing summary statistics on those groups, which used to be kind of complicated to do before dplyr, but with dplyr it's pretty simple. So I have this hint here. Look at the data transformation cheat sheet, and the functions mutate, group by, and summarize. These make these analyses pretty expressive and straightforward to do. And RStudio, by the way, has great cheat sheets. These little front and back sides of sheets, print them out or just keep the PDF, but they're super useful. So to solve this, first I need a new column that actually has the fraction using contraception. So you recall that this data set had 2 columns, using and not using. So I'm going to make a new column. That's what mutate does. It mutates a data frame or a tibble if you're using tibbles, but it mutates your table by creating a new column. So I'm going to mutate cues and create a new column called frac using, which is equal to using over using plus not using. And those of you looking on the web at examples of other things, you'll find a lot of code that's not using dplyr, that's using base R, and that's me. Honestly, I've used base R for most of my programming life. And there are other ways to do this. It's just that this way it makes it very easy for someone to read and imagine what you're doing, even if they don't know R at all, which is one of the great things about these tidyverse things. So sorry, I have to load library dplyr first. Now I can do this, and here's my Qs2, and I have this new column called fraction using. Easy peasy. In the old thing, it would have, in the base R method, it would have been something more like Qs2 frac using, I'll call this one 2, equal to Qs2 using over Qs2 using plus Qs2 $ not using. That should produce, if I did it right, it'll produce all the same answers, and it does. So those are equivalent ways of doing the same thing. Now I'm going to group by age and summarize the mean of the frac using column by age. Again, very expressive. Anyone even who doesn't know R could probably tell you what you're doing. You're taking your data set, Qs2, you're grouping it by age, and you're summarizing the mean of the fraction using contraceptives. And you'll see that because it's grouped by age, we now have only 4 rows because there were 4 ages, and we have this mean frac using column. Qs2 looks the same. Didn't do anything to it there. This, by the way, this funny percent greater than percent is called a pipe, and it sends the results of one thing to the next. So it's kind of a logical way in the tidyverse world and in dplyr to think about taking the results of each analysis and feeding it on to the next one without having to store this in an intermediate variable. So this all could have also been done in one step using the pipe. So in this example, I do the mutate, I pipe that into group by age, and then I pipe that into this summarize mean frac using. And this produces exactly the same result, but without creating that extra Qs2 variable, which, by the way, maybe I'll go ahead and clean up because I'm not using it anymore. Doesn't really matter, but okay, second question. Write on paper the model for expected probability of using birth control. Okay, so I'm first going to use use a logistic regression to create the model. You don't need to use paper to create the model. But then I'm extracting here the coefficients. Let's see what this looks like, bcoef. So there are the coefficients. And now I didn't exactly use paper here. I went ahead and used LaTeX formula to write this out, and in the built version of this you can see this written out in nice formula. I don't think I can actually execute this here. I would have to do the knit in order to show it to you. So maybe I'll let that continue in the background. But what I'm doing here is doing the inverse logit function, and then I'm just writing out my regression formula. Here's the intercept formula plus the coefficient, or sorry, the intercept coefficient plus the coefficient for ages 25 to 29 times whether the dummy variable for ages 25 to 29 and repeating for each of the additional coefficients times the dummy variable for that variable. My knitting is done here, so I can go ahead and show you what this looks like written on paper. Here it is, inverse logit. The coefficient is minus 1.13 plus the coefficient for age 20 to 29 times the dummy variable. So this is 0 if for anyone who is not aged 25 to 29 and 1 for anyone who is. And then I wrote on the next function just what the definition of the inverse logit function is. So after you go and do this, you have to apply the inverse logit function, which is 1 over 1 plus e to the minus x, x being whatever you calculated here. Okay, next question. Based on this fit that we just did, the logistic regression fit one, what is the expected probability of an individual 25 to 29 years old with high education who wants more children of using birth control? Calculate it manually and using predict fit. So calculating it manually, you could just plug it into this formula. So it would be minus, maybe I'll go ahead and do that. It's minus 1.13 plus, let's see, someone 25 to 29 years old, so that's 0.39. High education, so where's that coefficient? Oh dear, why do I have an NA here? I'm going to have to, I'll look at that in a minute. But since it's high education, I don't need this anyways right now. So that's irrelevant. And someone who wants more children, I have to subtract minus 0.83. So that's the log odds. If I do 1 over, let's see, what was that inverse logit function? 1 plus exp minus, so I'm getting a probability of 0.17. Let's see. So here's another way to do it, the more computational way, the less manual way. I created a new data frame called new data that has the data that I want to predict on. So age 25 to 29, high education, and wants more children. So this is in exactly the same format as what we would have found in the Q's data set. It has to be exactly equivalent. It can be a row directly out of the prediction data, or it can be a row that didn't exist there. And then I can just do predict one with the new data equal to this. This in this case is called new data. It could have been called anything else. I'll just give you an example. Also, by the way, it doesn't matter whether you use equals or this left sign. They're the same here. Usually I like to use this sign just to make it look different from these equal signs. And I'll call this, just to avoid the confusion of new data equals new data, I'll call this Q4 data. And then this would be Q4 data. And 0.22, okay, so I made some small mistake here. I trust this more than I trust my manual calculation. Let's see. All right, with a slight pause here, I'll show you the mistake, and I'll tell you, believe me or choose not to, that I made a little mistake on purpose to see if you were paying attention and to show you troubleshooting. So when I looked at this B coef, the coefficients that I created, here are the correct coefficients. And in this, we have a dummy variable for education high, whereas here I put education low. So when I loaded the data this time, I actually had a different reference category. I had low education as the reference category instead of high education, and I didn't update the later code. So I'm going to update this to education high. And now this should be correct. And also, if I use the correct coefficients from here, I should get the same answer as I did. This predict is pretty foolproof. But now I'm going to go, let's see, minus 1.13 plus 0.39 plus, now this needs to be, for education high, I need 0.32 minus, and then for once more children, 0.83. And now I have the same answer with my manual calculation as with the original one. And I'll update this in the on the course GitHub website as well. Actually, instead of just telling you that I'll update it on the course Git website, I'll do it right now. Why not? It doesn't take long, and it'll show you a bit about why I like to use Git and GitHub. So it shows you that I've changed this file, vignette session lab. I can click here to see the diff. This is the differences that I've created. So you see the correction that I made here from education low to education high to reflect the new reference category and the dummy variable of education high. And also this change I made here going from this sort of awkward looking new data equals new data to this new data equals Q4 data for question 4 data. So that looks good. I'm going to say correct education reference category coefs. I'm going to commit, close, push. And then that's all there is to it. That is now updated on the session 3 website. That's going to get automatically moved over to the BIOS 2 main website as well. It'll also get automatically updated on the course's Docker image and places where that is being used. Okay, enough of our little tour into GitHub. Let's go on now. This is a little more of the same. Let's go on now to this next question on predicted odds ratio. Based on fit 1 relative to women under 25 who want to have children, what is the predicted odds ratio for a woman 45 to 49-year-old who does not want to have children will be taking birth control? So this is not just a probability now, this is asking for an odds ratio between two of the groups. So as we saw in the lecture, we can get this just by subtracting these two coefficients. And since this question only asked for the odds ratio, we can just do that. So it's an odds ratio of 7.55. This, of course, doesn't tell us, doesn't give us a standard error or a p-value on this. So if we wanted those, we might want to use the multicomp package or another approach to doing inference on this this different coefficient that we're interested in here. And don't worry, we will have a chance to play with some model matrices later in this lab session. All right, next question. likelihood ratio test. Using a likelihood ratio test, is there evidence that a model with interactions improves on fit one with no interactions? All right, so we have our fit already with no interactions. Let's just take a look at that again. Right, it has all of these main terms with no interactions. Now we're going to fit one that has all interactions. So this is age, education, and wants more children with all two-way and three-way interactions. So I'm going to fit that, do a summary. And now we see we have lots of interaction terms here. We have all these two-way interaction terms and then several three-way interaction terms too. But the question just asks us to compare these two models. So not all of these individual ones. And we see that among all of these, there's only one slightly significant 0.0436 p-value interaction term. But let's take a look at the ANOVA. So this is ANOVA of fit1 with fit1.int. That's our fit with interactions. Test equals LRT. And look at that. Even though the individual interaction terms were fairly marginally significant, the sum total of them is quite significant. P-value of less than 0.001. So which, if any, variables have the strongest interactions? I make a nice package here, or a nice table here, using Stargazer to compare, to look at the output. So this looks best. This looks best in the HTML output. Let's go here. We saw all of these a little while ago here, so this is just kind of a nicer view of it. So this was comparing these main effects in the model with no interaction to the main effects plus the interaction terms in this model with interactions. So the question was just, which of the interactions are strongest? Well, looking down here, it looks like age 40 to 49 with high education is one of the stronger ones. And high education and wanting more children is also one of the stronger interactions, with either one increasing the effect of the other. And you could get that same information out of this table here. Okay, last question. Contrasts between every pair of age groups. Create a model matrix for a fit on age only with contrasts between every pair of age groups. And between which age groups is the contrast significant? So this is something that is obviously different from what we've been doing, because with the model formula approach and the default model matrices, we've just been getting comparisons for each age group against the reference category, which we've had as under 25. So this is asking for all pairs. So how do we do it? I actually give a few ways to do it. One semi-manually with this multcomp package. So I start, here's a fit and coefficients. This is a fit just with the age categories. And now I create this contrast matrix for use with the multcomp package. So for these 4 coefficients, I set up contrasts for each of the differences in age groups that I wanted. So 25 to 29 against minus 25, 30 to 39 against under 25, and with each one I'm defining here what the difference is between the original coefficients. So for 25 to 29 minus the youngest group, I need to take this 25 to 25 minus the intercept. And then I'm just repeating that, and I'm doing that basically manually here, and then using the multcomp package to refit this model with these coefficients, and then return all of these estimates, and now I get standard errors and z-values and walled test p-values. Pretty nice, hey? There is an easier way, also with the multcomp package. If you take a look at the documentation for this package, and I'll do that right now, let's see. Make sure multcomp is actually loaded. And then I'm going to go, so I could have gone question mark multcomp colon contermat. But once it's loaded, I can just go question mark contermat, same thing. But you'll see there are all of these different types of contrast matrices. I don't even know what all of these are, but I think they're, yeah, you have to look at one of these references to know what all of these contrasts are. Grand mean is comparing everything to the overall mean of everyone together, so no reference group at all. The one I want is the Tucky contrasts, which is all pairwise. So I can just look at that. It did this same thing for me, and I didn't have to type that. So the only thing is it's not quite as informative, the rows here, as it was before. It was a little easier to read when I actually defined the row names. So you might want with one of these to, to look at, so if I look at coef fit, you can see what these mean. 2 minus 1 is age 25 to 29 minus the reference group, etc. Okay. So there are plenty of, as I just mentioned, other contrast schemes provided here. And my only point of typing out this example contermat is that this is kind of a handy shortcut for running the examples that are in a function. So I could do this by copying this code and running it over here. This just does that for you. It copies it all over and runs it, and it gives you an example of running several of these different types of contrasts and showing you what contrast matrices it produces. So that's all for today. I hope you found this useful, and you will be able to take advantage of the things that you're learning here for the rest of the course, because they apply to all kinds of generalized linear models as well as to survival analyses. Thank you.